So in this question, we see what appears to be a ball bouncing. We've got a ball at a height before it's dropped, and then it bounces upward. And this is like a couple of other problems we've done in the class in our FRQ practice. So what we do here first is we recognize there's a change in height. So in understanding this, we've got that to that. And we can say then that we know, we're thinking when we see changes in height, we're thinking about conservation of energy. So we have our gravitational potential energy, so EPG, EPG is 1/2 m h, no, it is mgh, it is mgh1. And we see then that gets converted to kinetic energy at the bottom, which is 1/2 mv squared. And then what we see afterward is that there is new kinetic energy. So we'll call that kinetic energy 2, which is 1/2 mv2 squared. And we could see right off the bat the velocity is going to be different because of this conservation of energy. And that is going to lead to our gravitational potential energy, which is going to be mgh2. So what we see is that there must be a loss of energy, of kinetic energy. And so what that means is V1, which is over here, is greater than V2. And that smaller V2 then means there's less kinetic energy to be converted to gravitational potential energy when it rises. And so there's a loss of kinetic energy, and that could be due to, thermal energy, it could be sound, it could be vibrational energy. It could actually be that there's an impact crater which does this. It does work by lifting this up and increasing the potential energy of dirt on either side. There's lots of ways that energy could be transferred there. So let's see now what the question's actually looking for. So it's released from rest. Okay, so that's good for us to know it was rest. Let's add that up there. V0 equals 0. Actually, let's make that blue to code in with our initial information. So we have V0 equals 0. And the ball reaches the ground. It bounces to travel the height h2, as shown in the figure, in a clear, coherent paragraph response that may contain equations and drawings explained using the conservation of momentum and the conservation of energy y. Now, so everything we used to look at this, we applied conservation of energy. We made no mention of momentum whatsoever. And so this is something that would be striking. Clearly then, the AP in their rating is going to be looking for conservation of momentum in this description. All right, so they want some discussion of this in the description or in the explanation. Now, what's interesting is when we annotate a diagram like this, this can actually serve as our diagram. So we can talk about, we can reference step 1 where the energy is gravitational potential. It transforms into gravitational kinetic, or goes into kinetic energy. Third, there is kinetic energy. There is a loss of kinetic energy upon impact that goes into thermal, sound, and vibrational, which causes that loss of kinetic energy means that the velocity afterward is less, right? And then so that lower velocity means that there is a smaller kinetic energy, which means there's less energy available to reach a higher height of the gravitational potential energy. And so we can use this diagram as indicated in 1 above, or 2 above, 3 above. All right, so again, we've expounded on the energy, but what's going on with the momentum? Well, so remember when we define a system, and we see that in a system, if the momentum of an object is changing, then it is an open system. And when it's an open system, it means that we haven't properly defined it to include all the bodies involved. So if we see this object over beforehand and we see it dropping, we say its momentum is increasing. That's a sign we're missing something. And that thing that we are missing is the Earth. If in the beginning the velocity is 0 and the velocity of the Earth is 0, and the ball starts to fall and it now takes on a velocity, well, the Earth takes on a velocity so that the total momentum of the system remains constant at 0. So the momentum of the system remains 0, and it must remain 0 afterward. So after the collision, the object hits the Earth, but it has less speed. So that means that some of its momentum must have been transferred to the Earth. That some of the momentum was transferred to the Earth. And if some of its momentum is transferred to the Earth, then its velocity will be less, which goes along with the idea that the kinetic energy is less. And so now we've accounted for all the parts. So our answer might look something like this, where we say, before the bounce, there's a couple ways to start. One is to just start saying overall that the fundamental energy, we could say, and then we can go into explaining why. It's usually better to do that because if we come out with the right idea and explanation in writ large, then the rater doesn't pay as close attention to all our detailed explanations later because they know we've got it. All right, so we could start out by saying H2, or the ball reaches a lower height after the bounce, H2, than its drop height at H1, because energy, kinetic energy, is transformed into non-mechanical energy during impact, and momentum being transferred to the Earth both of these changes result in a smaller velocity after the impact than before. Since the law of conservation of energy dictates that gravitational potential energy transforms to kinetic energy at the ground, and EK is lost during impact, there is less kinetic energy after the collision, after impact, to convert back into gravitational potential energy, and thus the ball does not bounce as high as H1. So we go back. We have mentioned conservation of energy. Did we mention conservation of momentum? Both these changes, because EK is transformed in mechanical energy, impact and momentum being transferred to the Earth. Both result in smaller velocities. Form dictates ground transfer impact. There is... all right, so we have mentioned momentum, but we haven't mentioned conservation of momentum. We've spoken about conservation of energy, and we need to say more about the conservation of momentum. So we could say to track energy through the event, we have gravitational potential energy becomes kinetic energy. And that kinetic energy becomes kinetic energy prime plus Q and others. And that becomes gravitational potential energy. And this is time 0, before impact, after impact, at H2. So we define what's happened there. And now we could do that to track that through the momentum. And momentum we have P0 equal to P, and that is of the ball and the earth. And then afterward, we have the momentum of the ball prime plus the momentum of the earth prime. And so this is before impact and after impact. And so now we have made clear statements about conservation of momentum, conservation of energy. We have drawings, and we could say even next to this formula, say C drawing above 1 through 6. And so we're now tracking the entire thing. So now we go